And do you
And now we're in the next video. We were just talking about defining the position and the velocity of the person. So how do you think we should do that?
So I guess one thing that I think about right away is trying to break things down into the x and y coordinates just on the actual graph itself. So I might even use a different color and say if we're looking at our position vector, we know it has an x component that's along the x-axis, so rx, and then it also has a y component along the y-axis, ry. And the same goes with the velocity vector, vx and vy. So
Okay.
that's where I'd start.
Right, so then we might be able to say, okay, if I were going to write my position vector, could you just write this for me? I can't get this stupid thing off.
So the position vector itself is made up of maybe rx in the I hat direction, because it's along the x-axis, plus ry in the j hat direction.
Okay.
And the same goes with the velocity vector. So vx and vy.
Right. And notice there's a relationship between Vx and Rx, right? Vx is the time derivative of Rx, right?
Right.
And similarly, Vy is dry by dt. Yeah,
So that will definitely be useful information for later.
cool.
Okay, so at this point, I think it might be of interest. We'll spend more time here later, but just to talk about density briefly before we dig into some equations of motion and actually how our person is moving. So one of the things we're going to have to take into account with air resistance is that it changes with respect to altitude, as we also mentioned. And so that altitude really comes into the density piece. So we know the density is different at sea level than it is at 100 kilometers or at the boundary of space. So we'll just need to remember that that's going to also come into play. But it's not necessarily coming into a play as a time derivative, at least at this point.
So do we have some idea of like what, if we were going to draw a graph of that, what would that look like? The density is how does that density vary?
I don't know if I could draw it for you, but it decreases over
Well,
as
then you
altitude
can draw it, right?
So it might look like something. So the density as your altitude.
So the altitude is going to be Ry, right?
Right. So as Ry increases, so we're going to actually say, we'll keep density here, and as Ry is increasing, your density is actually decreasing. So it would look, we're just going to say something like this, but that shape is not exactly like that.
Right. So we could but we could look that up online, right? And we could probably, like, one of the things you could maybe do is figure out what this value is. Like, what's that value?
So at sea level, it's approximately about 1.2 kilograms per meters cubed.
So 1.2 kilograms per meter cubed.
And this is what happens when you have an aerospace engineer working on a problem like this at the boundary of space. It's very, very small, so 5.7 times 10 to the negative 7 kilograms per meter.
That's just sad.
Yeah.
Wow. Like, you didn't even have to look that up, did you?
Okay,
You
I
just-
did look that up.
Oh, okay. All right.
It's been a while. Okay, so now I think we can actually get into the equations of motion.
Okay.
So we've talked a little bit about going back to what, in our picture here, what our different position vectors are. We have our interactions, but we have to kind of think about how do we bring those all together to show how, in equations of motion, we're looking at how change in position is taking place, so along Rx and along Ry, and what at a particular point in time our Vx and our Vy are.
So we're going to get some differential equations here that we're going to eventually, I guess, put into ODE of 45 or something.
Something. So equations of motion. So one of the first things we can do is think about, well, if we sum the forces, what does that tell us? Well, it actually tells us the time derivative of momentum. So that is the sum of our forces on our person. So we're going to be looking at how does momentum change over time for this person as they're going through the atmosphere. And we know that's impacted by two forces, force of gravity, as well as the force through the air. And we've already defined those. So this equation is very nice to just pretty much copy over from what we had before. So force of gravity and air resistance. V hat.
Okay, so I think I understand everything on the right-hand side here. Like, I could imagine, like, v squared, for example. I could imagine how to figure out v squared. That would be like vx squared plus vy squared.
Right.
Right? v hat, we'll probably have to come back to, but I think we can figure that out. But what about this dp by dt? How do I write that down?
So one of the big key things is going back to our assumption that, well, first off, what is momentum? So momentum has two components. One is mass and one is velocity. And so if you rewrite this, you have ddt of mass and velocity. And you have to ask yourselves, are both of those variables changing? But we just said mass is constant. So there's only one vector in here. So this actually gets rewritten as the time derivative, mass times the time derivative of velocity vector, which we can rewrite based on what we did before, just as mass times the time derivative of vx I hat plus vy j hat.
All right, cool. So if I look at this, I've got now a differential equation that tells me how fast vx and vy are changing as a function of the gravitational constant, right, and as a function of the drag. And one of the things I think is kind of worth pointing out here, that, can I steal that for a second, is actually that what I've got here is not one equation but two equations, right? Because I actually have a vector on the left equaling a vector on the right. So if I write one of the equations, right, I'll write m times dvx by dt, right, the mass times the acceleration in the x direction, is equal to the sum of forces in the x direction. Well, the gravitational force doesn't give me any force in the x direction. There will be some x component to this force, right? So it'll be 1/2 rho cd a v squared, and then whatever the x component is of the direction of the velocity.
Right.
Right? And by the same token, and I need a negative sign there, by the same token I'll also get m times dvy by dt is equal to minus mg, and then minus 1/2 rho cd a v squared vy hat. And you can now see why it is that Alexandra is writing everything right now.
So before we get too carried away with our equations of motion, why don't we flip over to another video so that we can come back and look at what these vx hat and vy hat are.